All right, welcome. So in this video, I want to continue with our discussion on recursion and recursive analysis, but I just want to sort of up the stakes a little bit by, like we did earlier when we were talking about iteration, move into more complicated algorithms or in particular sorting algorithms. And so the one that I want to look at today, again, is insertion sort, but recursively. So here I have the sorting problem that we've introduced in a previous video. And here is my example of some insertion sort pseudocode, but tackling the problem from a recursive position instead of a iterative position, which we can do as well. And there's certainly a way you can implement insertion sort with two nested loops is the common way to do it. If you don't want to use recursion. But we're looking at recursion, so let's look at this example here. We can see that there is indeed a recursive call inside here. And maybe let's just take a moment to inspect that recursive call a little bit closer. We can see that that recursive call here has a size n-1 because we've reduced it by eliminating that last element. So what does that mean? What happens here when we call insertion sort on this? Well, again, trusting in recursion, assuming that we've implemented this properly, then what insertion sort does is it sorts the list, and at the end it returns us that sorted list. So what we should expect happening here is if we give it this list, which is a sublist of our input list, and we call insertion sort on it, then that function should return, as expected, a sorted version of this list. So what do we get? We get these n-1 elements back, but we know that they are sorted in order. Okay, so we kind of jumped here, so I just want to look at this first line, make sure we didn't miss anything here. This is, of course, our terminating condition saying, hey, if our list is small enough, we just return it. It's already sorted. So we know that when we've got here, that means the first thing we do for a non-trivial input, a list that's not already sorted for us, we will sort this sublist. Okay, so we pick it out, sort it, and assign it to this, this new temporary variable named a prime. Then I'm going to use a little notation here that's similar to an object notation in a language like maybe Java or C, C++ or C Sharp. In these types of languages, we might call the add operation. If you're more familiar with, say, like a JavaScript, it might be a push operation. Here, all I'm saying is take the element and put it on the end of that list. Now, one of the reasons I've chose to do this, we could have chosen to do a slightly different method call here. We could say call a method that I might call insert, which is exactly the operation that I'm going to try and do here, and where this sorting algorithm gets its name, insertion sort, is because we're going to insert this extra element, the one we left out, an, we're going to insert it into this list where it belongs. That's where we should insert it, okay? But this step here, I'm going to call add, meaning we don't insert it where we belong, we just add it on the end. And the little aside there I was sort of mentioning is we could have called a different one called insert that just does all this work for us when we call this. Now the reason I haven't called that method is because our purpose here is to do analysis. We want to know how many operations it's going to take us to do this recursive algorithm. And if we sort of hide all this effort inside that method, well, then I need to go and analyze that method as well and see how many operations does that method take. So instead of doing that, what I've really done is I've taken that insert method and I've just expressed it here in pseudocode. This is what the insert method would do. It would stick it on the end, and then it would, well, what does this do? I'll promise you it shuffles it down to where it belongs. So what we've done here, so let's look again. What we've done in this step, if we have a list of size n, we take off the last element, and then we take the remaining ones and we sort it, and then we took that last element and we stick it back on the end. Now if we're really lucky, if a sub n was the maximum element, it was, for instance, already in the right spot, then when we did that, we'd be done, and we wouldn't have to do anything else. It's already sorted. But more likely, a sub n, the element we just picked off the end there, because we just picked it, it could be any element in any of the ranks. It probably belongs somewhere else down below. And so we can think of these, since we've been talking a little bit about worst case and best case scenarios and so on. The best case scenario is, as I just described, maybe it was the maximum. We don't have to do any other operations, and we'll see in a second this loop would immediately terminate. Or we can think about the worst case. What about the worst case? The worst case would be we'd have to shuffle it all the way down, meaning maybe it was the minimum element, the smallest element, so we'd have to shuffle it all the way down. And then we might also talk about a different case, which is the average case, which is maybe how far we might have to shuffle it down on average. Well, that's around the middle, because we don't really know where it belongs, but half of those spots are below the middle and half of them are above. So on average, we'll probably have to go to around the middle. Sometimes better, sometimes worse, but on average, some around the middle. Or we can even pick out specific cases. We could say, well, what if it was the third minimum element? Well, how many swaps would we need in that case? So that's one way we would calculate the average, is by iterating over all those particular instances. But what we're mostly interested in is the worst case. And remember, that was shuffling all the way down. So let's consider that, and let's see how it impacts this loop down below. So now what this loop down below is supposed to do, as I've mentioned a couple times now, it's supposed to do the shuffling down below, which means we probably have to do two things. A sub n, we want to compare it to its neighbor, a sub n minus 1, and see if they're out of order. What does it mean out of order? Well, let's go check our definition up here. It says this should be in increasing order. So if the element we put on the end happened to be less than this one here, that's out of order, so we should swap them in that case. So let's see what happens here. Well, we set our j to n, okay. We compare those two elements, like I said. And then if they're out of order, if aj is less than aj minus 1, as I said, then we do our swap. Okay, so everything I mentioned there works, except let's look at the other pieces I kind of skipped over here. This bit here, well, that's just our out of bounds check. It's just making sure that we're going to get all the way down to the bottom and not run off the end of the array. I actually noticed on my other slide that this was an error, a typo, and it helps when you sit down and you work and you talk it out. So that's what I'm doing here. I'm talking it through, and I notice, oh wait, we're not supposed to go off the end here. But that would have gone off the end if we were equal to 1 there. Let's just make sure. If we were equal to 1, then we would have had aj is less than a0. So aj in this case was 1, 1, a0. We would be off the end. There is no a0. So that would get us an out of bounds. Now, one thing is in implementation, we probably would run into a case where that would give us a segmentation fault or some other kind of error, that out of bounds error that says, hey, you're not allowed to do that. But in pseudocode, you don't get any such errors because, of course, we don't compile them. And so instead, sometimes when you get an out of bounds error like that, we'll usually just assume that the implementation does whatever is the most obvious thing for it to do. Instead of crashing, because crashing is what computers do when they don't know what to do, but algorithms are for humans, and humans usually can figure it out. If there was a little bug like that and they say, oh, well, we'd probably just correct it like I did, or we might say, well, maybe when it goes out of bounds, it returns zeros, or it returns minus infinity, or some other value that makes sense for the algorithm that we're usually just allowing it to go out of bounds so that we don't have to do a whole bunch of error checking in the pseudocode. We'll leave the error checking for the implementation details where we need it. We don't need it up here, where mostly our audience is going to understand what we mean. Now, in this case, I made an error. So let's go back and double check. I made an error in this bit here where I said we should go down to j equals 1. Well, here we're actually going to stop. If j is greater than 1, we will continue. But if j equals 1, we will pop out. That's because that means we've shuffled all the way down to the bottom, and we've moved a sub n all the way to the front. There's nowhere else to move it, so we will stop in that case. And remember, that was the worst case that we mentioned there. So that was our possibility for the worst case. The only other line I didn't talk about was this one here. Well, here we're just going to do j minus 1, j equals j minus 1, which means we're just going to set ourselves up for the next iteration of the loop. Now, that, of course, is necessary because I've set this up as a while loop instead of a for loop like we've done in a lot of our other examples so far in this video series. So here, a while loop, which means we might have to be a little bit more careful when we get around to doing analysis for this, which is really the next thing that I want to do. I don't think there's anything else for us to see. Let's just maybe take one last bird's eye view of what we did. So the recursive algorithm, if it's not our terminating case, we will break off one element, a sub n, sort the other elements recursively. So once we're done that, we get a prime and it's sorted. So now that we know that they're in ascending order, we will, this little bit of pseudocode, as we mentioned, shuffles that a sub n down into its location where it belongs, and then once we're done shuffling, we return that element. Okay. Now we might want to think one last time, what's going on under the hood? Well, in this recursive call, now that it's size a minus of size n minus 1, on the next time around we break another one off and another one off and another one. So what we end up doing here is first we will shuffle 2 down, then we'll shuffle 3 down and 4 down and 5 down. So you can think of this, the iterative version really just iterates down and shuffles one at a time into its location. We're really doing the same thing here recursively. All right, now let's see if we can do a little bit of analysis. I've actually got sort of spoilers down below here, but let's actually, because this is a complicated enough algorithm, and in fact, we're getting to the level where it's so complicated, it's usually beneficial for us to stop doing such fine-tuned analysis where we're counting every single operation. Instead, it's usually a good chance when we start getting to this level of complexity that we might want to start renaming things like this 11 as C. And here we mean C as a constant, some constant. Maybe it's 11, maybe it's 8, maybe it's 3. But we're just going to give it a name because we don't really care what it is, whether it's 11 or 8. Someone does, probably somewhere, but asymptotically we don't care. And it just simplifies our math to stop counting every single one and carrying these constants together and always having to add them and multiply and so on. Instead, we get to start doing simple constant math, which is take a constant, multiply it by a constant, you just get another constant, or divide it by a constant or add it to a constant, you always just get more constants. So at the end, after doing all the operations, if you got some ugly mess of constants, you just give it a new name, call it C prime or C sub 0 or C sub 10 or whatever new variable name you have, and that makes it again easier to just carry forward in your math as just one term instead of, again, some ever-growing or ever-changing constant through your math. Now, with that said, I still have numbers here. I still have actual values here, and that's because I am going to nitpick every single operation, or try to at least. But the other benefit of moving to constants that we would gain is that if you count your operations slightly different than me, and you don't count 11 here, you count 10 or 12 or 15, I don't know. If you're counting more, then the C hides these differences, and we come back into agreement when we just say, well, it's a constant, right? It doesn't matter if it was 14 or 11. Again, someone might care if it's 14 or 11, but a lot of the time we don't. And so that gives us a way to just, if we have little off by one disagreements or even off by one errors, maybe we made an error, those ones are usually swept under the carpet and no longer matter. But let's see if we can go through and see what we come up with. Now, the other thing we'll notice here is this is a little bit ugly in the terms that that it's got recursive bit and it's got a summation over here. That's pretty much all of the mathematical tools that we've been working with so far in this series of videos. So let's see if we can, again, verify and make sure that this is correct. So first of all, let's start on the easy bit. If n is less than or equal to 1, hey, that's the terminating condition, so I think we got that right. How many operations? Well, 1 to come in the method, we usually count that. 1 to do this check, and then 1 to do the return, we're out 3. 3's been what we've been getting in most of the videos so far when we've been trying these different recursive algorithms. And well, hey, if it's not broke, then let's keep it. Okay, so 3 seems to work here. Well, what about the rest? Okay, now remember this recursive bit for the n greater than 1, I usually split it into 2 pieces. The recursive stuff, how much recursive work do we do? And then how much other work do we do? Okay, and over here the recursive bit is, well, this recursive call. So let's just verify, make sure one more time. When we were talking about how this algorithm worked, we said this recursive call is of size n minus 1. That's why we wrote n minus 1 inside here. the size of the recursive work that we do is of size n minus 1. Okay, and again, remember that's common. It's one of the possibilities that we'll see a lot. We saw that in earlier examples, but the other one might be in n over 2. Dividing in 2 is another possibility. We saw that in our last video as well. So let's continue. So that's the recursive work. What else we have to do is the extra work, which is the non-recursive work, which I sometimes say is the iterative work, which in this case it is. We have a loop as well as recursion. This is an example where we sort of blended the two models that we're looking at. And so in this loop, we're going to use a summation to express that. Well, actually, we've got a lot going on here. So let's tackle the loop first. Okay, now this loop is interesting because it's not a for loop, it's a while loop. Now in the for loop, we always had, when we'd hit this line, we'd say, well, on this line we usually had a couple operations at least. One would be an increment or a declaration, and then the other would be the check. Well, in this case, we actually, in a while loop and other types of loops like a repeat until loop, these loops have sort of explicitly split out the initialization, the increment, and the check into 3 different locations. This is why sort of for loops are sort of a more mature looping structure that was developed out of these sort of older looping structures by realizing, hey, every time I set up these loops, I usually have these different components. Why don't we just list them all on one line for simplicity instead of putting them in these different locations? Well, that's, and again, the compiler will often take the for loop that you've written there with the for notation and turn it into this type of notation for assembly so that it's easier for the machine to operate. This is what the machine wants to see. But because we've sort of done this in our algorithm as well here, we've gone ahead and sort of pre-done that. We can see that our declaration comes ahead and we've got our increment down below here, and we're only doing checks when we hit this line. Okay, so that's one thing that we should say. So we're looking at this loop here, we're still working on this loop, and we're noticing that we've sort of broken the initialization out and we've put it out here ahead. Okay, so we'll need to be aware of that when we're exiting, and I guess I realize here I've got an end for here. That's just a typo. I won't change that now. This should say end while, of course. Of course, that's just the end of my loop. So let's continue. Let's see if we can figure out how many operations are carried out in this loop. Let's focus on this line actually for a moment. There's a lot on this line, and I don't want to miss them. This line seems to have 1 for the -1. It's got a check going on here, and it's got a check going on here, and then we do the logic AND of those before we do anything else with that, either exit or enter into our loop. So maybe let's see if we can count up how many are going on inside this loop. Now those are carried out every time. Okay, they are also carried out on this line when we exit. So that's important. So we said 4 up there. What else do we have? 5 for the -1. I'm going to count swap as 6, but remember this is one case where we really should go in there and look. It might be more. It probably is more. Okay, I'm counting that as 6. And then we have 7 for the minus here, and then 8 for the assignment here. So that's where I got this 8 here. So I think we're good with this 8, or at least if you agreed with me on that, this is the 8 we've got here. But what about this? I've got these numbers here. Let's see here. How do we know what values we should put in the start index and the end index for our sum here? How do I know it's 2 and n? Well, first of all, what values does j actually go through in this loop? It starts at n, and then it goes down every time. Shouldn't we put j equals n to 2? Because I think 2 is the last one, right? J greater than 1. J equals n to 2. That's what the loop actually does. Well, the loop can do that. The code, the pseudocode, we can count down if we want to. There's nothing saying we can't. But summations, there are. The rules of summations say that, there's a couple rules. These indices have to be integers. We also have to count up. And so counting up is the important bit here. So all I've done is if I've identified my indices here as n and then counting down to 2, I just swapped them here so that we count up instead of down. And that's usually the trick we do when we have a loop that's counting down. We'll just swap them. Okay, as long as we're counting down by 1. All right, if we're counting down by something else by 1, or counting up by something else by 1, then that again gives us a little bit of trouble here because we have to count up by 1. But since we were counting down by 1, I just swapped them. Okay, so that gave us the 2 and the n. Okay, so let's continue now and look at see if we can get this 11. So this 11 is probably going to be related to those ones, but it's all the other ones that are carried out other than this loop. This loop was carried out by this sum. So again, we already entered and we said 1 to get into the loop, 1 to do this check. Okay, 1, 2. I'm going to count here 3 for the assignment and 4 for the minus 1, but nothing for this. We've already handled that with the t n minus 1 term here. Okay, and then we're going to do this add. Now again, this is another method called, just like the swap here, how many operations. I'm going to count it as 1, but it's a constant, I know that, but what the constant is I don't know. So this is again another good place where switching from counting 1, 2, 3 to counting, C, D, E might be better. Okay, so I'm at 5 right now. I'm going to keep going. This is going to be 6. Okay, now the loop here was covered by this, but I still need to exit the loop, and that was these 4 operations again. So I count those again. So 6 plus 4 is 10, plus my return statement is 11. So that's where I've got my 11. So hopefully you agree with me on counting those numbers down, that this recurrence relation right here expresses it. And then all I've got down here, this smaller one, is just a simplified version where I just said, hey, look, we know what this is. The 8 will come out. And then how many terms are there in this sequence? Well, 2 up to n. Well, there's n minus 1. We left out the first one, right? So there's n minus 1. So that gave us 8n. That's for the 8n. And then minus 8. Well, the minus 8 plus the 11 gave us the plus 3. So this is our simplified version. And all right, so I think this is the one we're going to move forward with. This was just sort of scratch work as we were going. Okay, so let's see this one. Now again, there's a couple things here that make this one interesting and a little bit more tricky. And the key one here is, instead of just having a constant out here, we now have this 8n as well. And that's going to, well, just make things a little bit trickier. Now, as we did in the last couple videos, when we got to this step, what we started doing is we said, well, let's just plug in some values. Let's plug in some values and see what we get. So we could start out easily. T of 1, we know that one, we just read it off. T of 1 is 3. Okay, but now, earlier it was a little bit easier to plug in values. Now it looks like it's going to be tricky, but if we're careful, maybe, again, the purpose of plugging in values here is to see if we can guess a pattern. And if we can guess a pattern, then we can, I don't know, see if we can prove it using one of our tools, our main tool, induction. So let's keep going. Let's try T of 2. T of 2, plugging in 2. Well, according to this, that's going to be T of 1, okay, 3 plus, well, we got the other 3, so I'm up to 6, plus 2 times 8 is 16. That looks like 22. Okay, that was a little bit strange, but not too hard. Okay. What about our T of 3? Well, now T of 3 is going to be T of 2. Good, we have that one. It's 22. Okay. Plus, what? What's this term going to be? That'll be 8 times 3 now, which is 24, plus 3. Now this T of 2, remember, was 22. So adding that all up gave us 49. Okay, 3, 22, 49. Now, we're trying to find a pattern here. Now, I'm pretty good with numbers. I like numbers. I don't really see anything yet. I'm starting to find patterns, or I'm trying to find patterns. And all I'm seeing here is 3. What's this? 3, 22. That's like 2 times 11. I don't know. This is 7 times 7. That's cool, but that doesn't help me in my pattern. Maybe I should look at the differences. 3 to 22, that's 19. 22 to 49, that's 27. What do I know about 19 and 27? I don't know. I'm puzzled. I don't know. Maybe the next term will help me. Let's try T of 4. Okay, T of 4 is equal to T of 3. Okay, plus, and now we've plugged in 4 here, 32 plus 3. So T of 3 plus 32 plus 3 again. Putting that all through, maybe punch it in your calculator so you don't mess it up. I got to 84. Okay, again, how are we feeling? Do we sort of feel, do we notice the difference is, I don't know, I feel like I might be able to guess this if I try it at it hard enough, okay? And maybe the reason I feel confident I might be able to guess it is because I think I kind of know, like I'm cheating, I know what it is, so I could maybe follow the right guess paths down and be like, oh, I just made a guess, but just be guessing the right thing. That's kind of cheating, okay? Like for one thing I might do is it looks like this plus 3 we've got on here. Let's just minus 3 from everything. That might make it a little bit easier, and that would give me 0, 18, 46, 81. Some of those are already sounding a little bit closer to what I a pattern I might be able to predict. But let's keep going. I've got one more on here. Let's say t of 5. T of 5 is t of 4 plus, well, it looks like 40 plus 3, so 43. These numbers here are really the ones that are worth looking at because we do see a pattern here, this 8n, but how is that combining with this other recursive term to get us this? Okay, this 127 is interesting. That's another interesting number. I mean, it pops out. It's 128 minus 1, which is a special number in terms of powers of 2. But again, I don't really see a pattern here. Okay, and it's growing fast, kind of. It's growing not linearly because the gap between each one is not the same. It's growing. The gap between each one is growing as well. And that's something we need to, take into account. And so how can we find this pattern? That's a good question. I'm not going to go into the details of that. Well, that's not true. I am going to go into the details of it right now, but I'm not going to try and just try and follow along with me instead of trying to, come up with it on your own. The idea is we're going to start kind of at the other end. Okay. Now, in my other video series, Design and Analysis of Algorithms, if you jump into that, we're almost done. You're almost at the end of this video series. So when you're finished this one, you're going to be pretty well prepared to jump into that next one. And so I encourage you to do so if you're interested in it, because in that series I do talk about in more detail techniques to take something that looks like this and try and come up with a good guess at what the closed form expression might be, or what the bounds might be, which is more likely what we're going to be talking about in that video series. So let's see if we can put a little bit more effort in here to see what we can come up with. Now this is, again, just see if you can follow along with me. Don't try and replicate this on your own necessarily. I mean, if you feel like it's pretty comfortable, then go ahead and do so. But really, I just want to lead you down a mathematical path and see if you can get there to the end and say, aha, yeah, I think I understood how we got there. Okay, so what I'm trying to do here is show you how difficult it can be to try and come up with an exact closed form expression for this recurrence relation. So let's go ahead and do that. Now what I'm going to do, this is an example of substitution, or trying to unwind my recurrence relation by applying it to itself. So I'm going to start with this version. Now, at this point, I'm assuming n is large. How large? I don't know. I'm not going so far as to say it's infinite. Of course, that doesn't really make sense because then the output is just infinite. That's not what I'm asking. But let's say big. How big is up to you. Okay, at least, I don't know, 2 is as big as I want it for now. But probably at least, like, say 10, because that's big enough that I can unwind it a few times and still kind of look at it. Okay, now we're unwinding it from the bottom. That would be a bottom-up calculation. We were trying to calculate the values of t from the bottom up. Well, here we could also try and calculate the values of t from the top down, and that's the technique I want to use here. So what I'm going to do is I'm going to take this definition I've got here and apply it to itself. So what does that mean? That's saying if I know what t of n is this, then I can ask the question, well, what is t of n minus 1? Well, t of n minus 1 would be, follow through, if I plugged in n minus 1 here instead of n, I would get n minus 2 and plus 8n minus 1 plus 3. So here I've just applied that. Again, I'm taking this term and I'm replacing it with what t of n minus 1 is equal to. It's equal to t of n minus 2 plus 8n minus 1 plus 3. What's this? Well, this is just this stuff coming down. Okay, coming down for the ride. Okay, now, I know we're probably tempted to say, oh, great, algebra, lump all this stuff together. We're going to get 16n and a bunch of other stuff. This technique doesn't work by doing that. Remember, we're trying to find a pattern. So instead, what we might want to do is draw circles around these two and say, no, this one should be isolated from this one. This was the first term that popped out. This is the second term that popped out. Follow me down the rabbit hole one more step, okay? Because now we can say, well, then what is t of n minus 2 equal to? Again, plugging it into this formula here, we could see it would be t of n minus 3 plus 8 times n minus 2 plus 3. So again, I'm going to replace this term here with that. Okay, t n minus 3 plus 8 n times n minus 2 plus 3. And then all the rest of this stuff came down for the right. And again, the purpose of this technique is to try and identify a pattern. So far, I think if you're with me, we can kind of see it. The 3 showing up every time. We've got 8 times something. And the thing that we're multiplying 8 by keeps going down by 1. And that's the pattern we're trying to identify. I bet if we did this one more time, we could probably guess what it would be. T n minus 4 plus 8 n minus 3 plus 3, and so on, right? Okay, now, when you get this far in the technique, we say, okay, I don't want to, keep doing this forever. I could do this forever and just get a really, really long line. Once I've identified this pattern that I think I have coming along here, then I want to generalize. And generalize means, well, what if we did this I times? Okay, so doing this one time ended up with an n minus 1. Doing it 2 times, we had n minus 2. And then 3 times n minus 3. What if we got to a point where we had done this so many times we got to t of n minus I, for some I bigger than 3? Okay, then the way we might write this is as follows. Let's see if you can follow along with me here and make sure that this is the same. So what I want to do is maybe just plug in 3 for I and see if we got the same thing we've got up here. Okay, so if I plug in 3 for I, well, at least I got the t of n minus 3 term. That's this one. And then this sum is trying to capture this pattern that we were looking at over here. And remember this pattern, if we start lumping them together, it was 8 times something plus 3, 8 times n plus 3, 8 times n minus 1 plus 3, 8 times n minus 2 plus 3. And in fact, what we can see is the pattern of what we're multiplying 8 by, too, is n minus something. Here it's n minus 0, so it's maybe hard to see. It's invisible. This is n minus 1, and this is n minus 2. And so I've written this here as n minus j. So each of these terms can be written as 8 times n minus something, and that's my j here, plus 3. Okay, so that's the formula or the pattern that I think I've identified in these terms that are popping out here. Now I have to decide. I picked j because I already have an I. I've already used I for something else, so I picked j, but now I need to decide what indices do I iterate j over. Well, I need to go back and look at my terms and be very careful. Okay, my first one here was a 0, n minus 0, so that's where I got the 0 from. Now the last one here, now remember, if 3 is our I, then the last term we get is the n minus 2 term, so that would be I minus 1. So that's how I got my I minus 1 up here. These terms keep counting down, technically, because we're minusing, until we get to exactly before the recursive term. So we got to 2 here, and then we got 3. If we went one further, we would go down to 3, and so on. So this term is meant to express our recursion down to somewhere into the middle of the pack. If we keep going, any of the levels we recurse down to, remember we did it 1, 2, 3, we could now plug in 6 and figure out what 6 is, or we could plug in 20 and figure out what level 20 would look like. And we'd have a whole bunch of these. The more we unwind it, the less recursion we have at the bottom, and the more sum we get. And we can keep unwinding until we get no recursion left at all and just sum. Well, when is that? Well, that's when this term eventually gets to an n small enough that it's 1 or less, but it should hit 1 first. So I'm going to say, let's keep going, wind down, until we get to a point where this term is t of 1. when is that? We have to decide when is that? What value of I would this be true for? Okay, well, if we had the value of I of n minus 1, then we would get n minus n, those would cancel out, but then we would get minus a minus 1, which would turn into a plus 1. That's what we want here. So that means the I we need is n minus 1. So plugging that in into our other instance of I gave us n minus 2 up above for our sum. Now that we get here, guess what? Our t of 1, that's 3. So that's going to be easy. We can simplify that by just swapping it out for the 3. And now all we need to do is apply our summation effort to this sum to see what we get. So this trick I did here, I usually call it algebraic unwinding or repeated substitution, or algebraic substitution is more commonly what it's known for, is a technique to unwind the recursion until there's no recursion left and there's just a big sum. And this is a standard technique for analyzing recurrence relations. And now all we have to do is use our summation method. So this is just practice in what we've already looked at in an earlier video. So let's continue with this. So now what we need to do is we want to decide how are we going to tackle this. I'm just going to bring it up here to continue on the right-hand side. And the first thing I think, there's a couple different techniques to use here, but I'm just going to do sort of a straightforward brute force attack at it. I'm just going to distribute my sum over my 3 terms. So that's going to give us 3 sums. Let's be careful. This sum, we took the 8 times the n, and that gave us 8n. The next one's going to be the 8 times the j, which gives us 8j, but let's be careful, that was a minus j. I actually factored the minus out here and put it out front. We could have put a plus here and then said minus 8 inside here. I don't like that notation, so when there's minuses, we often factor them out and put them in front. It just makes the notation look nicer. And then here, well, we just have that last term left over, which is the 3. So we just summed over the 3. Now, of these 3 sums, this one and this one are going to be probably the easier ones, so I'm going to start with those. But let's do to all 3 sums, factor out anything that doesn't belong to j or doesn't depend on j. So this doesn't depend on j, the 8 doesn't depend on j, nor does the 3. So we'll factor those out. The 8n comes out, the 8 comes out, 3 comes out. Now that we have them out, we just need to tackle these sums. Now these 2 sums are the same. From 0 to n minus 2, how many elements are there in that list? If we had started at 1, there would be n minus 2 elements, but we started at 0, so there must be n minus 1 elements. Likewise here. So we're going to get we're going to replace this sum with an n minus 1 term, same thing here. That leaves us with this term here as well. Well, this term is one that I call Gauss's sum, or it's also known as an arithmetic series. That's one that I talked about in an earlier video as well. The only difference is in an earlier video, when we encountered this, usually when we encounter this, the normal form has a 1 to start out, because otherwise we're just adding 0. Adding 0 to things doesn't matter. So we could right at the moment scratch this out and write 1 if we want, because that's exactly the same sum. But also, we usually go up to n, or even n minus 1. By n minus 2, you maybe don't have a formula for that. You might want to derive it yourself. Okay, I'm just gonna write down what it is here for simplicity. Okay, if you remember, this is how I do it. You take the top one and you add it to the bottom one. That's one of your terms, and n minus 2, and then what we're going to also do is take the top one minus the bottom one, but then plus 1 more. That's the n minus 1. That gives us the other term. Multiply them together, divide them by 2, and that's what this sum is equal to. Now, what we have left over then is this 8 out front. It was actually a minus 8, so the minus out here and the 8 up here, that's where that 8 come from. And then also out here, we just simplified. Remember, I said this was just going to turn into an n minus 1 term. This was just going to turn into an n minus 1 term, and we're done. Well, we're not done. We're done with eliminating sums, so now we just have algebra. So algebra, I'm just going to multiply through first. Blah, 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 blah. So 8n squared minus 8n here. We got the 8 over the 2 turned into a 4, so we got minus 4n squared. This is a little bit of binomial math, so double check my binomial math, make sure I got things right there. Okay, and then And again, with the minuses and the pluses, make sure I got the minuses and pluses. You know, we all can make an error just in that kind of math. And then over here, 3 times n minus 3, looks like we got that one right over there. And then, well, gather and lump our like terms together. We can do our 8n squared minus 4n squared. Okay, 8n squared minus 4n squared. That gave us 4n squared. I guess I jumped ahead of myself there. And what about our n's? Are we going to end up with 7? We got 12n here. Plus 3, that's up to 15, but minus the 8 gives us our 7. Okay, crossing those off leaves us only with our constants. The 3 and the minus 3 cancel, so that gave us the minus 8, and that's where we are there. Now I mentioned, double check my math, make sure I didn't mess up. It's possible I could have messed up in one of those steps. How do you know unless you double check? But I have double checked, so I do know I got this right. How did I double check? Well, a couple things I did is, of course, the next step is if this is the actual expression, then you should be able to prove this by induction. And indeed, I want you to try that, but I'm not going to do it with you. So we've done enough of this type of proof that you should be able to do this one yourself. And I've done it myself on the side because I just wanted to make sure I could do it. And it's actually fairly simple. But go ahead and do that. But instead, I want to practice what we've been looking at in the last video, which was strong induction. And I want to see, or not just strong induction, but I want to try and prove induction with bounds. And in this case, I want to do both. I want to practice our strong induction and then do an upper and lower bound proof. And I will leave that for the next video. So thanks for watching, and we'll see you in the next video.